So good morning, everyone. Thank you for being here. So I have been given by the organizers the task of trying to review the physics of primordial and low metallicity star formation. And now clearly this is a very fundamental problem if we want to really understand this picture of increasing complexity, because the first stellar populations are going to really set the stage for all the physical processes that will then drive the evolution of the first galaxies that we are currently observing with James Webb. And despite the fact that, as Martin said, this is a relatively young field of research, at least for some of us 25, 30 years ago, there has been a tremendous amount of work in trying to really improve our understanding of the physics of low metallicity star formation. And despite, my efforts, I'm sure that I'm not going to be complete, so I apologize for that, and I will refer you to excellent reviews that have been written on this subject, including the very recent one by Ralph Klassen and Simon Glover that definitely has made my task easier. So I will start from an historical perspective on this problem, and the very first question that we want to answer is how small were the first cosmological objects? And this was actually the title of a seminal paper written by Tegmark and collaborators back in 1997. Where they, following the evolution of density fluctuations with a detailed understanding of the physics of molecular hydrogen, they tried to constrain the parameter space in terms of critical dark matter halo mass that could host the first stars as a function of redshift. And in fact, you see here this yellow region of this parameter space that is excluded simply because H2, molecular hydrogen, is not able to cool fast enough to really trigger the formation of the first stars. And you can recognize here these two diagonal lines that mark the transition from molecular cooling halos, the so-called mini halos, and atomic cooling halos, where the primordial gas can cool because of collisional excitation of atomic hydrogen. Now, if you compare this yellow region with this diagonal line that shows the redshift evolution of 3 sigma peaks in the cosmic density field, you find this spot here, the star, that gives you that at redshift 30, the first star-forming mini halos should have a mass of the order of 10 to the 6 solar masses. And this is actually the two figures that we all have in mind when we think of the very first places in the universe where star formation starts. Now, this very important study has then revisited, including additional physical processes. And one of these that has attracted particular attention is the effect of streaming velocities between the baryons and the dark matter. We know that these stem from second-order perturbation in the density field, and at redshift of around 30, the streaming velocity is of the order of 1 kilometers per second, which is very similar to the virial velocity, to the circular velocity of these small mini halos. And so clearly this is expected to reduce the baryon over density in these mini halos to suppress cooling, and therefore to delay the onset of star formation, raising this minimum critical mass of dark matter halos where star formation can start. And you see here, again taken from the recent review by Ralph and Simon, the status of our understanding of the impact of streaming velocities. The yellow line is the minimum critical mass in the absence of streaming velocity, and for some of these simulations, you see that the increase in this critical mass is significant and may lead to a delay of the onset of star formation, leaving also imprints on the topology of the first radiative sources, and hence also to the onset of cosmic reionization and the 21 centimeter signal. Now, another interesting aspect is the nature of dark matter. We have heard a bit on this in the nice talk by Pratica the day before yesterday. She was working under the framework of warm dark matter. Here I show another example of fuzzy dark matter models where the dark matter is made by very light axions with very light masses, and this again leads to a suppression of structure formation in the smallest mini halos, leading again to an increase of this critical mass and a delay in the onset of star formation. And in this paper a few years ago, Sullivan and Irano and Volker-Braun have shown how this, can be constrained by current and future observations. So what you see here is the critical mass for CDM, showing 4 sigma, 3 sigma, and 2 sigma peaks in the density field. And this is compared to what you expect for a fuzzy dark matter model with different axion masses. And you see that there is this shift in redshift, this raise in the critical mass. This region here of the parameter space is constrained by observations, near field observations. We will hear more about this in the next session. So you have these smallest halos where you actually, the smallest galaxy, ultra-faint dwarfs, where you can actually measure or constrain the mass of the host halo. So this gives you clearly a maximum possible mass for this critical mass for the onset of star formation in the universe. And then if you look at this gray area, again, this is the constraint that at that time we had from the 21 centimeter absorption trough from the edges collaboration. We know that this is probably now has been significantly revisited and probably excluded by more recent observations. However, it gives you an idea of what 21 centimeter observations may do in terms of constraining the onset of star formation in the universe. And if you look at this intersect between these two lines, clearly this seems to exclude the lightest amount between the two axion dark matter models. And so I did this exercise yesterday, so to put this in a more recent context of observations of high redshift galaxies with JWST. So if you look at the highest redshift galaxies that we have now at redshift 14.3, and if you consider an estimated stellar age of 100 million years, this then dates back the onset of star formation in this system at redshift 19, which is very close to one of the two borders of the putative 21 centimeter absorption trough in the edges signal. And so again, if this is true, and as we will get more observation of this kind and better constraint on the ages of the stellar population, this may become even more constraining. This already excludes even the heavier among the two fuzzy dark matter models. So this is really a proof of concept of what we might be able to do in the near future in terms of constraining fundamental physics with these observations. So there are also additional important physical processes related to the effect of radiation fields early on, such as the Lyman-Werner UV background. We have heard about this in some talks yesterday. As you increase the Lyman-Werner background, you photodissociate molecular hydrogen and suppress cooling. So this, of course, leads to an increase in this critical mass. Here you see the critical mass as a function of the intensity of this UV background in this strange units that you will keep on seeing probably in the rest of the session. And so a collection of data, again, taken from this recent review. And as you can see, depending on the strength of the UV field and also on the resolution of the simulations, the effect of cell shielding, which is very important in order to prevent photodissociation in the densest systems. You can have huge variations in the resulting critical mass for the onset of star formation. And here again you see a similar effect, but this time due to the positive effect, positive feedback from X-ray photons that instead increase the free electron fraction, promoting H2 formation and cooling. And so if you look at this complicated plot, to summarize, what you find is that if you have very strong UV radiation, then of course this raises the minimum mass to host a formation. But if you have moderate UV background, you can effectively counteract this effect with X-rays and then decrease the minimum mass to form the stars. So this is really complicated physics, interplay of different physical processes, but most importantly, these two effects clearly depend a lot on the nature of the first illuminating sources. So what is the stellar mass spectrum? What are the kind of supernovae exploding? What are the kind of black hole remnants that are left over from this very first stellar generation? So clearly, this need requires to make a step backward and try to understand, to constrain what is the nature of these first stellar populations. So again, this topic has really boosted in the past 20 years, starting from these very pioneering simulations done around the early 2000s. This is a particular example from Naoki Yoshida, where actually they were able to to follow the process starting from cosmological initial conditions. So you consider one of the first mini halos that forms at the intercept of cosmic filaments. You follow H2 cooling in these mini halos, and you can track the first phase of collapse of the cloud, and it's very nicely driven by the physics of molecular hydrogen, completely driven by the physics of H2. So you see the formation of this dense core, and this can be traced to the point in which you have the non-LT-LT transition in the level population of H2, and the cooling becomes less efficient. And then from this point on, the cloud continues to collapse inward without fragmenting until it forms a central protostellar core with a mass of 10 to the minus 2 solar, which is then accreting gas tremendously from the surrounding environment and growing the star from the inside out. And this can be really very well understood looking at the simple diagrams showing the temperature versus density track from a seminal paper by Kazuo Mukai. And you can also already see what is the huge difference between the metal-free case and when you have a metallicity comparable to the sun. So now the star grows inside out by accreting gas from the surrounding envelope, and so it's clear that even the accretion rate strongly depends on metallicity. So if you compare the predicted accretion rate in the primordial case with the enriched case, you have several orders of magnitude of difference, and so it was clear from the very beginning that the final stellar mass will be set by an interplay between accretion and protostellar feedback onto this accretion. And in fact, the first radiation hydro simulation in 2D run by Takashi Ozokawa and collaborators showed clearly that if you include the effect of radiative feedback from the growing protostar, you're going to have a significant suppression of accretion. You see here the difference between the no feedback and the feedback case in terms of the accretion rate versus stellar mass. And in this first simulation, the prediction was that the final stellar mass would be of the order of a few tenths of solar masses. Now, this is one single halo. Shingo Hirano and collaborators readdressed this problem, looking at a large family of different halos, trying to understand what was the impact of the environmental conditions where the collapse was occurring. And by looking at the collapse of the highest density peak in each of these halo, he was able to derive this mass spectrum of solitary pop-tree stars, one star per halo, but gives you an idea that the spectrum of possible masses is really large. It varies between tens to thousands of solar masses, and also by comparing the blue and the red, you see the impact of Lyman-Werner radiation that suppresses H2 cooling, raises the temperature, and so shifts the mass to larger stellar masses because of the larger accretion rate onto these stars. Now, as resolutions of the simulations increased and computational power increased, it was clear that as you follow the collapse phase, you see the formation of this surrounding disk that around the primary star, which then becomes unstable, and so it forms several secondary stars, which then interact by merging, but also competitive gas accretion. So clearly the picture becomes far more complicated. So this was by Paul Clark, was one of the first simulation that showed that. Additional simulation run by Thomas Greif, who was a very talented scientist who made really important seminal contributions to this field, showed that actually dynamical interaction between the fragments are very important. He was able to follow the evolution only for 10 years. This was really a very, pioneering work. And showed that, however, the multiplicity of this system continues to grow in time. So it was important to push forward the integration of these simulations to better understand what was the final outcome in terms of stellar mass spectrum. And finally, Athena Stacy addressed the very important problem of understanding what was the interplay with radiative feedback from the growing protostar, and showed clearly that this was very important in order to reduce the final masses of this multiple stellar system, leading to formation of massive Pottery binary stars. Now, again, this was one single example. Takashi Ozokawa addressed this trying to look to several different mini halos with 3D radiation hydro simulations, and show that indeed you can have a large variety of different accretion histories depending on the environmental conditions where you sit in, having a final total stellar mass that ranges between 10 to the 3 solar masses. And also I think that this particular paper was very interesting because it pointed to very interesting physics that happens here, because disk fragmentation actually does not prevent the formation of massive stars, because you have fragment migration inward, repeated episode of accretion, which inflates the primary stars, and in this bloated state, the primary star has a reduced surface temperature, decreasing the UV feedback onto the surrounding gas. So you have a positive loop here, and fragmentation may lead indeed to a faster growth of the primary star. So finally, I just want to show you this nice movie from a simulation by Sugimura and collaborators, where they actually try to follow this disk fragmentation, including the effect not only of UV, of the feedback from the primary star, but also from secondary stars that are forming. And so I have to speed up, of course, the calculation, but you see clearly the formation of multiple stars. They interact, they merge sometimes, and they start to really inflate these large H2 regions, which then, of course, affect the dynamics of gas accretion and the resulting stellar mass. So the outcome of these simulations was the formation of a small cluster of stars with multiple binary systems, some of which have really interesting masses. As you can see here, these are very important and interesting masses for the possibility that this will lead to binary black hole systems, which then may merge and be potentially observable by gravitational wave telescopes. So there are far more physical processes that are very important: the effect of turbulence, magnetic fields, dark matter annihilations, and then again the strong Lyman-Werner radiation and X-ray background, which not only affect the minimum mass of dark matter halos that can host Pottery stars, but also affects the resulting mass spectrum. So clearly you see here tremendous contributions done by different groups to this field, and I, of course, do not have the time to go through them, so let me jump to the conclusion. The conclusion is that we still have a very poor understanding of the mass spectrum of population tree stars. And again, I borrowed this nice figure from the review of Ralph and Simon, where they select a subset of simulations and show what is the comparison between the predicted mass spectrum with and without the effect of radiation fields. And we can say that, of course, this depends a lot on the resolution of the simulation, on the integration time of the simulation. We have a huge variation in mass ranges, but of course, what seems to be is that you have a relatively log-flat distribution in terms of stellar masses, which makes it look different from present-day IMF, and so where you have a steep power law slope. So clearly this shows that you have a more top-heavier IMF as you go to lower and lower metallicity. And of course, this needs to be constrained even from observations, and I look forward to hearing more on this in the next talks. Now, of course, this uncertainty in the POP3 IMF translates into an uncertainty on the co-moving star formation rate density evolution of population tree stars, and I borrowed this from a recent paper by Alessandra Venditti, where she compared the result of her simulation with other large-scale, similarly large-scale and small-scale simulations in terms of the predicted star formation rate density evolution in POP3 stars. And as you can see, depending on the resolution of the simulation, the different physical input that they have, you have a huge variation, orders of magnitude variations in the predicted star formation rate density of population tree stars. And of course, this and it's an issue, but at the same time, you have that most of these simulations seem to indicate that actually the phase of POP3 star formation is not only confined at the very high redshift, but it has a prolonged phase through cosmic time. And this was already introduced even by Harley yesterday in his talk, and is probably due to inhomogeneous metal enrichment, but also to the complex interplay between radiative and chemical feedback, which can self-regulate the formation of POP3 stars. And I borrowed this sentence from a paper that we wrote with Andrea and Luca Tornatore in 2007, where I think that was really one of the first paper that showed, that tried to map this POP3, POP2 transition on cosmic scales, showing that indeed, despite the poor resolution of the simulation, we could follow this late POP3 star formation down to relatively low redshift. So Alessandra has made a detailed study of the position of the properties of these POP3 star forming regions at late times, that they may be hosted in the outskirts of massive galaxies in the epoch of reionization. You see here some examples. The red dot shows you the position of these pockets of POP3 star forming regions, and the mass fraction as a function of the host stellar mass at redshift 10-ish compared to what is predicted by other simulations, similar simulations by Kajima and collaborators, show that the fraction is very small, the POP3 mass fraction is very small, but you may expect these pockets of POP3 star forming region being powered by 10 to the 4, 10 to the 5 solar masses of stars. And so now the question is, do we think that we can detect these? Well, one possibility is to detect them through the helium-2 line emission. We know that this is very complicated. You have alternative sources. It's short-lived. It is affected by mass loss. I don't have the time to go into the details, but of course, we have some candidates, and this is very interesting that JWST may open up the possibility to really detect this late POP3 star formation. One candidate is this beautiful system observed by Eros Vanzella. It's a very lens system, very tight upper limit on the metallicity, huge under a lower limit on the equivalent width of the helium-2 line, so maybe too extreme even for POP3. Another candidate is GNZ11. We have this helium-2 clump displaced from the main source of radiation. This displacement is also predicted, is consistent with this idea that you have a peripheral POP3 region that is still forming POP3 stars. And again, a huge, large equivalent width interpreted as, cannot be interpreted as due to photoionization from the GNZ11 source. So doing a very sophisticated analysis in terms of photoionization models, the plausible conclusion is that it could be due to in situ photoionization from POP3 stars. And again, the last one is, the helium-2 emitter from Wang et al., where again they interpret this as potentially due to a hybrid population of POP3, POP2 mixture with POP3 powering the helium-2 line. So I think that this is a very interesting perspective that we should try to pursue in the coming years. And I think that Alessandra will better address in her talk what is the, however, what are the limitations and the difficulties that we have to overcome in looking at this peripheral region. So I have to jump to my conclusions. There are other indirect constraints that we will be hearing more on this in the afternoon. A possibility, very interesting possibility, is also the one of gravitational waves. So I look forward to discussing this more with you. And of course, just 1 second, of course, when we have the explosion of the first POP3 supernovae, then this set the stage for the second generation star forming regions. And of course, we have simulations that have tried to capture what is the nature of these second generation stars. And I think that we will hear more on this in Ken's talk and also in Sumyon's talk. Simulation clearly show that there is a transition in the properties of these second generation stars in terms of their mass distribution, and even relatively metal enriched systems at high redshift may have a tilt in their IMF, which could help at least relieve some of the tension with the mass to light ratios, decreasing the mass to light ratios in these very high redshift galaxies that we are currently observing. So I leave you with my conclusions, and I apologize for having been late.
Thank you, Raffaella. We're still finishing quite early.
Okay.
So we still have plenty of time for discussion.
We get some volunteers too.
Yeah. Okay, Andrea, start. If nobody else puts his hand up.
Well, thank you for the very nice review. One general question with POP3 stars that I'm asking you, but I'm asking myself and everybody, I guess, is the fact that in order to be seen, we always need to form a cluster of 10 to the 5, 10 to the 6 POP stars. POP3 stars. And so how do we, none of the model that you have discussed is actually able to do so. So how do we, what is your take on that? So how do we form 10 to the 6 star at the same time in 1 million year and all POP3?
Okay, so this is a very good point indeed. So I don't have, of course, a definite answer on that. I think that, so there are several aspects. One, the first thing is that actually the simulation that I was showing you concentrate on the collapse within an isolated mini halo that is sitting there. And of course, this leads, we see, to a small cluster of stars. As you increase the radiation field, however, then you push, you raise this critical mass to higher values, then the conditions change, because of course the gas needs to self-shield from the surrounding radiative field, and so the densities are typically larger. And what we clearly see, I think this has been shown by several simulations, is that as you change these environmental conditions, the masses, the kind of clusters that you form increase in mass. Okay, so you have a completely different mode. You have a much larger cluster of potential Pot3 stars. Then, if this affects also the mass spectrum, it's still to be understood. And in addition, in this late phase, I think that, again, the conditions are different. I mean, we don't really understand how this is working, at least not in our simulations. We are working on that, increasing the resolution. But the idea is that you have these small satellites that have not been able to form Pot3 stars because of the essentially suppression due to the radiation field or to feedback. And then as they be accreted onto a larger systems, then the gas get compressed and reactivate star formation. So again, one should really understand what happens in this particular environment, whether you can indeed are able to form these more massive clusters, or instead, as you were thinking, to a smaller cluster size, and then of course this becomes even more challenging to be detected, because of course it will affect the helium-2 luminosity. So I think it's a very different. A very difficult question to answer, because these are really particular environment, but we should definitely try to better understand this.
Okay, Priya.
Thanks for a very nice review, Rafa. So my question is, if you go back to the plot with the masses, the final masses, the IMF of POP3, is this, I mean, are we tapping out at 1,000, or is this going to keep going if the resolution improves?
Towards the high mass end?
Higher mass end.
I don't think, I mean, the high mass end, the reddish and yellow colors show the distribution when you include the fact of the radiation field. So you are not suppressing H2 cooling, but you are keeping the gas hotter, and this is why you shift this to higher stellar masses. I think that as you increase the resolution, you would probably be able to break these into smaller pieces, okay? Right. And so to really populate the whole mass range, but not really to push this to even larger. Of course, it depends on the environment that you are looking at. So I think that Sunyeon has very nice results on this. If you increase the background radiation field and then suppress H2 cooling, then the picture completely changes. And as you know, this goes into the direction of having supermassive star formation. And I didn't mention that because it was beyond my possibility in 25 minutes.
Thank you.
Question further back.
Hi, this is fantastic. I have a question about these massive POP3 clusters. How would you distinguish them from metal and slightly metal-enriched clusters with a top-heavy IMF, I guess?
So this, in terms of their observable properties, you mean, okay, so it really depends on the mass spectrum, first of all. So the mass spectrum will likely shift. You mean, how can we, what are the metallicity that you have in mind? This is the
like 10 to the minus 3 or something.
10 to the minus 3, it depends, I think that Sunyeon will show this. It depends on the redshift a bit, but above redshift 10, you still have a tail in the mass distribution according to the simulation. It's not completely log flat, but you have still a tail of massive stars. Of course, then you will have some metals. I don't know if this would be enough to lead then to unobservable predictions. The helium-2 line luminosity would still be high. I think that it's a good point. We should try to work harder to really understand if we, by looking at them, may be able to discriminate in terms of observable properties these two regions.
Thanks for a great review. So what does the silver bullet look like? I think a lot of us would be probably skeptical of a claim about a helium-2 line. Is it abundance patterns, or can you comment on what you think the most likely What will the first convincing evidence for POP3 be?
It's very hard to say. It's very hard. I think that we have to, to look to multiple evidences. So lack of metal lines is, of course, one of these. And in addition, the equivalent width of the helium-2 line is also an important indication. So I think that we have to build our arguments on multiple evidences, not to a single one. But it's, of course, very hard because you have always very likely an alternative possibility. One of these is the fact that you are not looking at a cluster of POP3 stars, but you are looking at, for instance, a direct collapse black hole. So, and of course, some diagnostic diagrams may help you discriminate between this possibility, but I think that we don't have a definite answer for that.
But are you pessimistic about abundance patterns in low metallicity stars or damp Lyman alpha systems, for example?
Absolutely. So I was referring to direct detection.
Okay.
So as an alternative, and not alternative, complementary possibility, looking at the abundance pattern is absolutely a very important strategy to pursue, both in distant DLAs and in nearby metal poor halo stars. I think that even in this field, we have a tremendous advancement in recent years, and I didn't touch that because we decided to split with Alex and Stefania the different enormous, very nice results that we are having now on local observations, but also observations of DLA. So, yeah, this is another very important positive work. Of course, we have to build our constraints on multiple lines of evidence.
And the last question was from John, and if the next speaker could come forward.
Thank you for the talk, and so very related question. So about the helium-2 lines, and so is it so maybe the first stars so reproduce strong helium-2 line, and is it due to top-heavy nature or so more likely related to that so smaller so stellar radius? Okay, so in the finite metallicity case, with the top-heavy IMF can also reproduce. So
exactly. So that's the point is how do you describe this? I think goes back to the question that Alex was asking. So how can you discriminate between the two? It's not clear to me. I think we have to better understand this.
Okay, thank you again to Raffaella.